Let us see another example of fixed beam. So the question is, analyze the fixed beam of span L subjected to a full UDL of W per unit length over its entire span. Draw shear force diagram, bending moment diagram, and elastic curve. So here there is a fixed beam whose span is L and flexural rigidity is EI, and it is subjected to a full UDL of W per unit length. So let us say this point is A and this point is B. We are supposed to analyze this fixed beam and draw the shear force diagram, bending moment diagram, and elastic curve. So the first step here will be to choose redundants. So let us choose reaction at B as one redundant and moment at B as another redundant. And we have the consistent deformation equations. Theta due to loads plus theta due to redundants is equal to 0, and theta is written as area of BMD divided by EI, and the other consistent deformation equation is deflection due to loads plus deflection due to redundants is equal to total settlement of supports, and deflection delta is written as area of BMD divided by EI multiplied by centroidal distance. So now we will have to split this beam into simpler beams. So we can split this into cantilever with full UDL, W per unit length, point A, point B, this is L and EI, and another cantilever with reaction RB, and another cantilever with end moment MB. And now we have to draw the bending moment diagrams for these cases. So for cantilever with full UDL, we get a hogging BMD of parabolic variation. So this is a parabola and we get hogging BMD, and the moment here will be W into L by 2, that is equal to WL square by 2. These are the points A and B. The span is L and flexural rigidity is EI. And for cantilever with RB, we get a sagging BMD with triangular variation, and the moment at this point will be RB into L, and this span is L, and these are the points A and B. And for cantilever with end moment, we get a rectangular BMD, which is hogging in nature, and the moment will be MB. And these are the points AB with span L. And now the centroidal distances have to be considered from the centroid till the redundant, from the centroid till the redundant, from the centroid till the redundant. These are the centroidal distances. Now we can apply our consistent deformation equations one after the other for each of these BMDs. So for the first BMD, the area of BMD will be minus half, sorry, this is parabolic variation, so it will be 1/3. It is minus 1/3 base into height divided by EI. For the second BMD, it is triangle, so it is plus half into base into height divided by EI. And the third BMD is hogging and a rectangle, so it is minus area of BMD will be MB into L divided by EI, and this is equated to 0. Now if we simplify this equation, we get RBL square by 2 minus MB into L is equal to WL cube divided by 6. So this is our first equation, in which there are two unknowns, RB and MB. So I'm simplifying these equations. I'm keeping RB and MB on one side, and this part is sent to the right hand side. I get my equation 1. Next, for each of these BMDs, we can apply the second consistent deformation equation by taking area of BMD and centroidal distances. So it will be, for the first BMD, the area is minus 1/3 base into height divided by EI, and the centroidal distance will be from centroid till the redundant, that is 3/4 of L. So this will be into 3/4 of L. The second BMD is sagging, so it is plus, the area will be half into base into height divided by EI, and the centroidal distance will be, for the second BMD, it is 2/3 of base, so this will be 2/3 of L. And the third BMD is hogging, so it is minus area of BMD is MB into L divided by EI, and the centroidal distance will be half of L, so this will be L by 2. This is equal to, there is no settlement of supports mentioned in the problem, so we can take it as 0. Again, here we have two unknowns, so we can keep them on one side and send the other term to the right hand side. So on simplification, we get the equation as RBL cube by 3 minus MBL square by 2 is equal to WL power 4 divided by 8. This is our second equation. So now here we have two unknowns and here we have two unknowns. So two equations with two unknowns can be solved to find the values. So now here, to solve the two equations, we can multiply equation 1 with L by 2 and subtract equation 2 from it. So this will give us equation 1 into L by 2 will give us RB into L cube by 4 minus MB L square by 2 is equal to WL power 4 divided by 12. WL power 4 divided by 12. And from this we have to subtract the second equation. So it will be minus RB L cube by 3 plus MBL square divided by 2 is equal to minus WL power 4 divided by 8. So the resulting equation will be, these two terms will cancel and we are left with minus RBL cube divided by 12 is equal to minus WL power 4 divided by 24. And from this equation we can write RB as W into L by 2. This is the reaction at point B, right? So now we have a fixed beam of span L on which there is full UDL of uh, W per unit length, and we have determined the reaction at B as WL by 2. Also we will have a reaction at A which we will consider as RA, and this can be determined by considering static equilibrium equation, that is sum of all vertical forces is equal to 0. So here we get RA plus WL by 2 is equal to W into L. From this equation we can write RA is equal to WL by 2. This is the reaction at point A. And also using the two equations we have calculated RB. So by substituting RB in any one of the equations, we can calculate the value of MB. So let us say substituting RB is equal to WL by 2 in equation 1, we get, so here in equation 1 we know the value of RB, so we can calculate the value of MB. So the equation will be WL by 2 into L square by 2 minus MB into L is equal to WL cube by 6. Here the only unknown is MB. So if we simplify this, we can find the value of MB, which will be WL square by 12, right? So here, along with RB and RA, we have also found the value of MB, which is WL square by 12. Okay, so now we can calculate bending moments at various points to draw the BMD. So calculation of bending moments by considering sagging moments positive. So here we already know at point B the bending moment is hogging WL square by 12, so it is minus WL square by 12, and at point A the bending moment will be, if we consider right hand side, so this will be hogging WL square by 12 RB into L, which is sagging, so that is plus WL by 2 into L, and due to the UDL it will be a hogging bending moment, that is W into L by 2, so it is minus W into L by 2. So this moment is calculated as minus WL square by 12. So this is the moment at A and moment at B. So now we can draw the shear force diagram. So this is our reference. At point A, there is an upward shear force of WL by 2. And from point A to B, there is a downward UDL of W over a span of L. So it will be WL by 2 minus W into L, which is minus WL by 2 in the negative region. And at point B, there is an upward reaction WL by 2. So this is minus WL by 2 plus WL by 2. So it becomes 0. This is positive and this is negative. And this is the point where the shear force is changing its sign. That point will be at a distance L by 2 from the supports, because it is a symmetrical beam. So now we can also calculate the bending moment at this point. So let us say this point is C. So let us take this point as C. So bending moment at C, if we consider right hand side, will be, so at this point let us consider there is a section and we are taking right hand side portion, so it is minus WL square by 12 because it is hogging bending moment, and RB into, so now this distance is L by 2, so it will be RB into L by 2, which is sagging, so it is plus WL by 2 into L by 2, and this UDL will be W into L by 2 into half of L by 2, which is hogging, so it is minus W into L by 2 into half of L by 2, that is L by 4. So this is calculated as WL square divided by 24, right? So now we can draw the bending moment diagram. So moment at A is minus WL square by 12, that is in the negative region. Moment at B is minus WL square by 12, that is also in negative region. And at midspan, moment at C is WL square by 24, that is in the positive region. So this is WL square divided by 24. And because you have complete UDL, you will have to join these points using parabolic variation, right? Above the reference is positive and below the reference is negative. And you can also calculate the location of point of contraflexure if required, right? This is the BMD, and elastic curve can be drawn after BMD. Point A, point B, this is point C. So this is point A, point B, and point C. So from point A till here it is hogging. So this will hog like this. And from this point of contraflexure till the other point of contraflexure, the beam has to sag. So it has to sag like this. And from this point of contraflexure till point B, it has to again hog like this. And these will be the points of contraflexure. So this is the elastic curve. So we will see some more examples in subsequent videos. Keep following.